Really? Put the thing back on it. It definitely will help it.
Put the thing back. Oh.
I'll just get started.
Yeah, you can just get started.
Okay. So once again, thanks for coming to our workshop on LT Spice. So we'll just be going through a few examples of
Sorry, everyone.
a few examples of simulations and how you might be able to get the most out of this software. Of course, like if you're on the computers in the labs, it should be there, but definitely I would recommend using LT Spice on your own machine as well, just to get used to it. But yeah, so we'll get started. Pretty much, we can just start off by making a new file. And what we're first going to do is just start with a few filters. Right, so let's say we have a signal, and we want to be able to process low and high frequencies differently, right? So in this case, we'll start off with just a low pass filter. So we want a system where low frequencies can pass through, but high frequencies are attenuated. And so what we can do is just create our circuit. So a lot of the symbols in LT Spice do have hotkeys. So for example, a voltage source is just V, a resistor is just R, and you can rotate these by using Control R. And also we have our capacitors, which you would probably guess is just C. And from here, we can just connect the circuit up with wires. Right, so pressing W, in some versions, the hotkey might actually be F3. In this particular version, which I think they're updating most systems to, now uses W. And, right, that's just my circuit. Something to remember as well is to connect to ground, otherwise you'll get an error. So you can just do that with the hotkey G. And that's our circuit. Right? So intuitively, what this should be doing is, well, you know that the capacitor tends to maintain the same voltage across it, right? And so in that sense, if I have a high frequency signal, this capacitor is gonna sort of counter that. Now, something I still have to do is define values. So this resistor here, now you can right click on any of these components and it'll come up with some menu. Now, where you click on the component is important. If you click on this R here, you'll see it says enter a new value. If you click on the resistor itself, you'll notice it comes up with all these things here. And if you click on this one, R1, it says enter a new instance name. Now, I mention this because sometimes you might accidentally click on the wrong part and change the name of the resistor, when in reality, you don't actually end up assigning a value to it. So R1 is the name of the resistor, and we can set the value of this resistor to, for example, let's say 1000 ohms. Now, you don't have to write the units, it automatically does that for you. So here I can just say 1K, and it'll automatically be 1000 ohms. Other abbreviations you might use include milli, so lowercase m, micro, which is just U, N, which is nano, pico, which is P. Those are the main ones. So we can just set that and be done with that. Same with the capacitor. We can set the capacitance to, say, 100 nanofarads. So just 100 N. And the last thing we have to do is just set up the voltage source, right? So in this case, we can create a variety of functions. So if you notice, what I did was I right-clicked on voltage source and clicked advanced. And so here we have this menu where we have a variety of functions. There's none, pulse, sine, exponential, and some others which you don't really need. For this, let's just investigate sine waves. Right, so we want to create a sine wave. And we have all these different parameters that we can use. So like DC offset, which I'm not going to use. Amplitude, which I'll set to 5. Frequency, which I'll set to 100. The other ones we're not too worried about. The time delay is just the time before, well, when you start the simulation, it's the time before the signal starts. You have your phase, the number of sine waves. We don't have to worry about those though. So that's our circuit, and we want to set up a simulation. The two main types of simulations we use are generally transient and AC analysis. So transient, as you might guess, is just to do with time. It plots the value of the voltages over a period of time. So I'll just pick 0.1 seconds, and we can start. Now you notice it comes up with a new window, and I can probe different points in my circuit. So for example, at the input, I have a sine wave, and we see it's also at has an amplitude of 5 volts, which is what I defined. Now, when I look at the output, I'll change the color for this. You can see that there is also a red line which pops up. That's our output. And you can notice that, I mean, these two frequencies are, well, these two waves are very, very similar. And this is actually what we expect anyways, because we're creating a low-pass filter. So, as I mentioned, we allow low frequencies to pass through, but let's say we want to test things with higher frequencies. So let's say I test 1000 hertz instead, and I restart the simulation. Well, first of all, you can see that we do definitely have a much higher frequency. So I want to zoom in just by selecting an area. And you can see at 1000 hertz, my output wave is noticeably smaller, just a bit. You might also notice that there is also a bit of a phase difference. So my output wave lags a little bit. That's because of the capacitor. And I can keep going. It's 10,000. Oh, I might change the time just a bit shorter as well. And you can see, once we have a higher frequency again, my wave gets even more attenuated. Right, so once again, that's the expected behavior for our low-pass filter. Now, this is useful because it allows us to see the shape of the wave itself, right? There might be other waves you might investigate, such as square waves or other maybe triangle waves, and you can see the actual shape of the wave. But sometimes, something else we might want to look at is the amplitude. So you'll notice how, as I increase the frequency, we get a lower output amplitude. But it's a little bit tedious to keep doing that for all different values. So what we can also do is actually run this simulation in such a way that we can actually find the output amplitude for a variety of frequencies at once. So that's to do with this, our second type of analysis, AC analysis. So what I'm going to do is I'm just going to set some values. I'm going to set it to decade. And I'll just put in some number like 1000. Usually you'll use decade. The other options like octave linear list, we might mention later. Starting frequency, I'll just run from 10 hertz to, let's say, 1 megahertz. Now, megahertz, interestingly enough, is not actually capital M, it's meg. So just to distinguish it from M, where M might be. I usually write it in capitals, but I think meg with just capital M might work. But test that out for yourselves. We'll just run this. Now, we'll come up with an error. Now, every once in a while, you can't run into errors with LT-Spice. Sometimes they might not be very useful, sometimes they might be. But this one here, it says no AC stimulus found. So the reason why we have this is because when we set up our voltage source, these functions on the left, even though we've set it up as a sine wave, these are actually only really used for our transient analysis. When it comes to AC analysis, all we have to do is just set this little box here. Right, so I can set the AC amplitude to just 5. So what this is going to do is it's going to test an AC amplitude of 5 for all different frequencies in my range. If you want, you can leave this part here, or you can remove it. And once we run this, we can see that, I'll change the color. For low frequencies, I start off with a fairly high output, and then after some point it starts to decrease. So that is the effect of our low-pass filter. In this case, it's automatically set to decibels. You'll be using decibels more so later on, maybe like you'll maybe cover it near the end of 2134, but you'll definitely use it more in 2133. But something that's more easy to understand, I guess, is just a linear graph. So I guess with logarithmic, that's usually to do with like multiples, but linear, we can see, is quite literally linear. And once again, same idea. This shows that the higher frequency there is, then the lower the output. Okay. Do we have any questions about this so far? Oh, yes, that's a good question. This one below is phase. So the axis on the left is our magnitude, and then this axis on the right is our phase. So, for example, at 1 kilohertz, we have maybe a negative 36-degree phase. And then you notice that it approaches negative 90 degrees, which from the capacitor results because of the multiplication by complex numbers, pretty much. But yes. Okay, any other questions? Yes.
We have two components there. Which one does the program run from? How does the program
Oh. Yes, so the one in blue is sort of, I guess, commented out. The one in black is the one that runs. Yeah. So I think it automatically selects which one to use depending on how you set it here. So you can right-click on these commands to change them. And in this case, when I set it to transient, you can see that transient automatically goes black. No worries. Yes. Sorry, what was that? I can't hear. How to send it back to AC. Yeah. Yeah, so right, I just set it to back to transient, but to set it back to AC, what I can do is just right click on these commands. It'll bring up the analysis configuration window, and I can select AC here and press OK. Yep. Set up the command, like these ones here, the values. Yeah. So with decade, the reason why I pick decade is because it's useful because it's logarithmic, right? So here, every time we move along, we multiply by 10, right? So it's 10, 100, 1,000, 10,000, 100,000. So that's why I set it to decade. Points per decade is essentially, I guess, the resolution of the graph. The more points it has, the more accurate my graph is, but in turn, it'll take longer to process. And then starting frequency and ending frequency are just my range of frequencies that I'm looking at. I might briefly cover list, actually. So list is something that you don't tend to use as much, but it's useful if you want to find details of the circuit at just one particular frequency, and you want to get information for all different kinds of nodes, like including all the voltages and the currents. So what I can do is do list, set a frequency, maybe 10K, and just click OK, and run this. And then it comes up with a window. And what this tells me is that at this frequency of 10,000, these nodes have these voltages and these components have these currents. It tells you the magnitude as well as the phase. Like I mentioned, it's not as commonly used, but it's definitely useful in some cases. Oh, yes, no worries. It's still an AC analysis, but it's just under the type of sweep. Yeah. So that's another thing that's also very useful. Okay. So this one was our low pass filter. Now, conversely, let's try building a high pass filter. Now, the configuration for a high pass filter is very similar. It's just that instead of the resistor up here, we'll put the resistor here and the capacitor here. So I'm just going to swap the location of them. I'll set some values, let's say 1 microfarad, and let's say 1,000 ohms. And I'll change my analysis back to decade. So 1,000 points per decade, 10 and 1 meg. And from this graph, looking at our outputs, we notice that this time, our low frequencies are fairly attenuated. And then as we increase our frequency, the magnitude increases. Right? So intuitively, how this should work is that any DC components of my signal should get blocked by this capacitor, right? So capacitor is open circuit under DC conditions or low frequency conditions. whereas the high frequency waves can just pass right through this capacitor, and hence that's what we find at our output. Let's see. And if I set this to linear, just to make it a little more intuitive, these are the actual voltages that we get at our output. And then, of course, this darker green line is our phase. So it starts off with a fairly large phase difference, and then at our high frequencies, that phase difference decreases. Do we have any questions about this? Yes.
Yeah. I think it's all as we have to finally aspects of the so sometimes this I give them like 3J object or
Oh, yeah. Yeah, you have to compute those manually. Yes. So the question he just asked was, if you're given capacitances or inductances in terms of J, in that case, you do actually have to kind of like go backwards and calculate the exact value of F that would be required for that frequency. Yes. Any other questions? All right. And on to the next exercise, just a band pass filter. Right, so what we've looked at so far is a low pass and a high pass filter. What we want to do is actually combine properties of both. So to filter out both low and high pass and high frequencies, what we can do is actually just cascade both of the filters that we have so far. So what I'm going to do is move this section across. So I just pressed the hotkey M to do that. And then I'll add my components back and join up the wires. And I'll set these values as before. Right, so you'll notice we have both our high and low pass sections combined together. And I don't think we have to change the commands for this. These commands all go good, so I can just run this as is. And selecting our output node, we see a very nice result. So low frequencies are fairly attenuated. Frequencies within a specific band can pass through, and then our frequencies that are higher than around here tends to get fairly attenuated. So that's our band pass filter, right? It's literally a band that passes through. Okay. All right. So those are the three filters. Do we have any last questions for this part? Okay. Is there anything else? I think so. Okay. I might go on with section 3 first, actually. So, section 3, this one part is looking at NE555 timers. So, it's not a chip that you'll use very often in your courses, but it's something that's fairly commonly used in other projects to create a square wave from a DC input. And you can imagine that's very useful because it would be fairly difficult to just turn DC into a square wave if you had to do that on your own, right? And having this chip is quite useful, especially in low voltage circuits. So what we can do here is actually just search up components. So there are all different kinds of components in this library here. You'll notice that there is also a hotkey, which is just P. So I can press P. And there are all different kinds of things here. For example, there are current sources, op amps. In this case, I'll just search up the NE555 chip. And it literally just comes up as a big block, right? And each of these are just our different pins. So I'll just put on the circuit from the notes real quick. So we have our ground, which is pretty obviously just connected like that. We have 2 voltage sources on the side, and I'll connect ground to those and set the voltages. Something that's also very useful is net labels. So oftentimes it's pretty inconvenient to draw wires in some cases, especially if you have wires going from one side of the screen to the other. So what you can do is just sort of create a net label, which we see has the shortcut N. And if I press N, I can create net names. So for example, Vin. And any points that I label with Vin are connected just without a wire. So in this sense, I've connected this point here with this point here. I'll just continue on with the other ones as well. So we have VCC. I want to connect these. Oh, yes. No worries. So as for after getting this one up, or just getting the chip up? Yep. So at the top, you have this one here, which allows you to search up components. And in this section, you have all different kinds of components that, yeah. Oh, is this the... Yes. So it's this one. Yes. Yeah. So if you have the other version of LT Spice, the shortcut is F2. But yeah. So I'll just finish off this circuit. We have a capacitor, resistor, oops, VCC ground, grounds, capacitor, wire. And I'll label this as Vout. Okay. I won't explain too much about this chip, but in summary, so with this particular pin trig, if I recall correctly, if we have an active low input to trigger, that essentially starts a timing cycle for this chip. So what I want to do, well, what I'm going to do for the in is create a very small low active pulse. So it's going to start as high, it's going to very briefly go to low and return back to high. And we can do that with a pulse. So initially, it's going to start at 5 volts. When the pulse turns on, I want it to go to 0 volts. I want the pulse to start a little after my simulation starts, just so we can see everything that's happening. So I can put a delay, in this case 3 milliseconds, so just 3M. The time for rise and fall, we don't really have to worry about. It just slows down the rise or fall pretty much. We have our time on, which I'll set to 200 microseconds. The period, I'm not going to worry about, and the cycles, I just want it to happen once. So I'm just going to set the number of cycles to 1. Alright, so you can see that all of these different options give us a fair bit of configurability for our pulse wave. And if you wanted, you could also create a square wave using this as well, by setting, I believe, the T period. But we'll just start off with a pulse for now and run a transient analysis. Oh, sorry, one moment. 10 and 1. Yes. And I'll just close the previous one as well. Right. So as I briefly mentioned, a low input to the trigger would sort of activate this timing cycle. And as a result, we see when this V in goes low, my V out goes high for some period of time. So this is what we would call a monostable, I get like a monostable output. It only just happens once, and then it returns back to being stable, which is just at 0 volts, right? There are other ways of creating monostable pulses like this. You'll learn more about that in 2133 as well. But this is just one way of achieving that.
Is there a key for just writing
Text. Right. It just says T here, so if I... Yeah, that works. Okay. So this is sort of one step of it, right? We're creating a very brief pulse output But as I mentioned, this chip is very useful for creating square waves. Now, there are actually quite a few different configurations you can use for this. There are plenty of different configurations you can find online. And they all have different properties as well. But we'll just use the one on the notes here. So I'll move these all to the side a bit and start rearranging everything. Okay, and this goes here. All right, that looks good to me. I'll just set this. And you'll notice here that, as I mentioned, we get a square wave output. Now, pretty much roughly what's happening here is like there's kind of like a feedback loop almost, where the voltage causes some of the capacitors to gradually charge and discharge. And then once it reaches certain threshold voltages, it flips over in the opposite direction. But you'll notice that this time, right, we don't have, we only have one voltage source. So before we had a manual pulse input. This time, we have an input here to the trigger from over here on the other side. In this case, something you might notice is that this square wave has a bit of a unique duty cycle. It's actually on for longer than it is off. As I mentioned, there are many different configurations for this chip which allow you to get different duty cycles. There are also some configurations that are more optimized at, for example, getting an exact 50% duty cycle compared to others. But this is just one way of simulating things, right? The point of this is to be able to simulate these chips in LT-SPICE. Do we have any questions about this? Okay. All right, so we'll go back to section 2, digital and analog. Now, this section probably is not as relevant to 2134, but it is definitely something that you might look into in 2133. the first thing we're going to do is just build a comparator. So this circuit takes in essentially two voltages and compares the two voltages. Depending on which one is larger, it outputs high or low. So one way we can do that is actually using an op-amp. Now, so far, most of the uses for op-amps have just been using negative feedback. In this case, we're not actually going to use the feedback at all. So the idea here is, I'm going to take some op-amp. A lot of the op-amps there are actually a lot of op-amps in LT-Spice. The reason for that is because in real life, different op-amps have different characteristics. And not only that, there are some imperfections in op-amps that are not necessarily ideal. So, in the notes, we've listed LT1721, right? It's just some op-amp model. I guess it just depends on the application, right? Because like if your intent is to simulate a circuit that you're going to use in real life, then you would generally prefer to use the exact op-amp model because it'll include some of those imperfections as well. But there are ideal op-amps that you can use. Some of them do require extra steps to set up. So, for example, we have op-amp and op-amp 2. These ones do require a bit of setting up, I think. We also have universal op-amps. Different types of 1, 2, 3, 3A, 3B, 4, 5. I'm not too familiar with all of them, but I think generally universal op-amp 2 is the one to use. I'll demonstrate the universal op-amp 2 in a moment as well, but we'll just get this set up first. So we'll have two voltage sources. One is going to be for one of the inputs, the other is going to be for the other input. So we'll have one for the signal, and I'll put that on the plus side. We also have another one, which I'll just have as VCC. And I'll put this through a voltage divider. I'm also going to set the positive and negative terminals for my op-amp. I'll just set that as VCC as well, and ground. And we have our outputs. So the idea here is that we've got a voltage divider taking in VCC. I'm going to just divide that by 2. Right? You can see 1K, 1K. In the middle, it'll be half of VCC. And then depending on the value of my signal, we can either output high or low. So let's say 5 and 2. If VCC is 5, half of that is 2.5, which is at the negative terminal. If the positive terminal is 2 volts, well, that means the negative input is greater. Well, the magnitude of the negative input is greater. And so what do we think we'll get at our outputs? Well, one way of thinking about this is our op-amp takes input and then applies a very large gain to it. So it's going to be some kind of gain multiplied by v plus minus v minus. V plus minus v minus is going to be 2 minus 2.5, so negative 0.5. And since it's negative, it's going to give us the lowest possible input, no, the lowest possible output. And our lowest possible output is just ground. So I should expect something around ground. So we'll run a simulation for this. And my output is 171 millivolts. So fairly small, fairly close to ground. The reason why it's not 0 is because, as I mentioned, different op-amps have different properties, and these are some of the imperfections that may arise. I can also probe my other points as well. So for example, V plus is at 2 volts, V minus is at 2.5 volts. And because V minus is at 2.5, well, V minus is greater, we get the lowest possible outputs. Do we have any questions about this section here? Okay. Something I might demonstrate actually. So, well, we'll try a few different values. So, our point of comparison is 2.5 volts. So I'm going to try different values. So let's say I have an input that's greater than 2.5. Well, now V positive minus V negative is positive. And a positive value multiplied by a very large gain from the op-amp is also going to give me the most positive, well, the largest value output. So when I run the simulation, now we have 4.819-ish volts, which is fairly close to 5 volts, right? So that's what our comparator is doing. It's comparing this value with some reference value. We can also experiment with putting other signals into this comparator as well. So let's say I put maybe a sine wave. Now, this is a little bit more in-depth, something that you might look into with 2133. But if you can understand this, it makes the use of the comparator a little more clearer. So here we have 3 different things happening at the same time. So it's a little more complicated, but our green wave is just our signal, our sine wave, that we're comparing against this fixed value of 2.5 volts. So that's the turquoise line here. Now you'll notice that any time my sine wave goes above this reference value, my output switches to high. And then anytime my sine wave goes below that reference value, my square wave switches back to low. This is one way, well, this is another way of generating square waves from other waves. You can do this with a triangle or a sine wave. Like I mentioned, you'll do this more in 2133. but I just thought it would be something nice to mention here. Okay, do we have any questions about this? Okay. Right, I want to see. Okay. So those are our comparators. Joe, do you reckon I should go through ADCs? We can take a look. All right. Okay. So the next part, analog to digital converters. Once again, this is more covered in ELEC2134, but the idea here is that when it comes to technology and interfacing technology with the world, well, on one hand, for example, things like microphones, this one I have right here, it takes in sound waves, and that gets encoded into what? That essentially turns into some kind of electrical signal. So the vibrations of the diaphragm of the microphone generates an electrical signal, and that signal we want to be able to turn into zeros and ones that can be stored in a computer. So that essentially is the goal of an analog to digital converter. It takes in analog signals from the real world and turns those into zeros and ones that can be processed by a computer. So an analog to digital converter is actually comprised of several comparators. So I'll just build this quickly. So I'm just going to copy these a few times. As you might imagine, copy is just Control-C. Interestingly, Control-X you might think is cut, but generally it works better just as deleting, in my opinion. So we can copy this a few times. And I'll connect these back together. So what this is doing here is we have several comparators. And you'll notice that by copying this comparator several times, my voltage divider gets longer and longer. So not only that, because it gets longer with many more resistors, each different point along this chain of resistors will have a different divided value. And that becomes the reference points for each of these different comparators. Right? So a little bit of voltage will be lost across the first resistor, and that'll become the first reference point. A little more voltage gets lost across the second resistor, and that gives us the next reference point. So we'll have several reference points, right? And then my signal gets compared with each of these. And so let's pick this is for something I accidentally connected all of these outputs together because of the net labels, so just be aware of that. And I think that should work. Yeah, okay. So with each of these comparators, let's for the very top one, let's look at the voltage here. The reference voltage is 4 volts. If my signal is above 4 volts, it's going to be high. If it's lower than 4 volts, it's going to be low. My signal is 3 volts. So V plus minus V negative is going to be 3 minus 4. That gives me -1. -1 multiplied by a very large gain will give me the lowest possible value, which in this case is roughly around 0. As I mentioned, there's the imperfections with these op-amps, which is why it's at 171 millivolts. In fact, I might actually get rid of these and put in universal op-amp 2. Just for demonstration. So universal op-amp 2 is an ideal op-amp. And so when I run this, we get something much closer to 0. 5 microvolts, it's pretty negligible. Now, as for the other comparators, so looking at those, the next one, the voltage at this one is, well, the reference voltage at this one is 3 volts. And the signal is also around 3 volts. In this case, these are so close to each other that honestly it might even just come down to like a floating point error. But in this case, my simulation is giving me actually, I'm just going to ignore this one for reasons I won't explain. 2 volts. If my signal is 3 volts, it's greater, so I'd expect a high output. And that's what I get as my blue line here. 5 volt outputs. And then the very last one, because of the voltage divider, my reference voltage is 1 volt. And as I've mentioned, the signal is 3 volts. Because the signal is greater, it becomes the highest possible value. So the idea here is we're taking some analog value as our signal, comparing it to a bunch of fixed values, and depending on that result, I get essentially zeros and ones as my output, right? Because 0 is low, 1 is high. That's one way in which we can convert analog into some digital value. Uh, hmm. Now, when it comes to representing this in bits, zeros and ones, so we have 1, 2, 3, 4 comparators. So that'll give me 4 different possible levels in which my signal can be. So if I have 4 different possible values, then one way you can think of that is that the data can be stored within 2 bits of data. So within 2 bits, you have 0, 0 or 0, 1, 1, 0 or 1, 1. And I can assign each of these results to some 2-bit binary number. This is more covered in ELEC2141. If you've done that already, that's very good. But I guess the point of the next part of this exercise is to just use logic gates. So with this, I guess it tells us the level of the signal, right? It can, well, in terms of the possible configurations, we can have either, if we have a very large signal, it'll all be ones. A little lower, these 3 will be 1, this will be 0. A little lower, these 2 will be 1, these 2 will be 0. And a little lower, this will be 1, these 3 will be 0. So we've got those different possible values. And I want to sort of map those to my 2-bit binary number. So with this is essentially something we call, well, we can do this with something we call a priority encoder. It takes the most significant bit from each of these, in which case, like, it's going to be the highest value, which is high. And based on that, if this one's on, I'll get 1, 1. If this one's on, I'll get 1, 0. This one, 0, 1. This one, 0, 0. That's what I want to do. So we can add some logic gates here. Hey Joe, can I just check something? When I search for OR, it comes up with this version. Just ignore the others? Okay. Okay, yeah. Thanks. So we'll do that. I'm just gonna copy over the schematic from the notes for this. So, and we have and 1, 2, 3, and not, which is inv. Yeah. The actual name for not in this and a lot of other softwares is actually inv, sort of like inverter, right? And I'll just connect these up. and add ground to each of these at the very bottom. Okay. And I'll put 3.5. This should be okay. Zero, one. This gets outputs to here. I think that's it. Okay.
The voltage level for logic sticks between 1 volt
Hmm.
in anti-flux.
Yeah. I'll just check what the 1 volt, yeah. So I think that's right. B1, B0. Should be. And in okay. Point 5. So 1. Okay, I think this is zero significant. Okay. I think this is right. Okay. So I've configured up some logic gates. I'm not going to talk too much about those itself or the logic behind it. But we can experiment with a few different values now. So let's say we have 4.5 volts. And between the reference points, so we had reference points 4, 3, 2, 1. So 4.5 is greater than all of those. It's going to give me all ones. And the greatest possible binary number for that is just going to be 1, 1. So when I run this, and I can see that both B1 and B0 are high at 1 volt. So let's look at some other values. So going down to 3.5. So now this time it's between 3 and 4. We would expect 3 1s and 1 0. My output should just be at 1 0. And we can see that B1 is 1 and B0 is 0. So that gives me my 2-bit binary number, 1, 0. Once again, going one level lower, I should get, well, 1 less than 1, 0 is 0, 1. So I should expect 0, 1. B1 is 0, B0 is 1. That's my binary number. And then testing 1.5. We have just 0, 0. Right, so with that information, we've essentially encoded some analog signal, put it through a bunch of comparators, and then turned that into some binary number, which we can store on our computers, process, and then share, upload, send elsewhere. But yeah, there are, I guess this is one way of having an analog to digital converter. There are definitely other ways as well. Some might be more effective, some might be faster. Also, something to note is that this one here, we only have 4 comparators with 2 bits. 2 bits is not a whole lot of information, and especially if you look at the specifications of things like microphones, which can have much more clearer detail, perhaps even upwards of 10 bits per sample. Those would require either many more comparators or maybe just a different arrangement of components completely, right? But there are many different ways to tackle that problem. This is just one of those. Do we have any questions about this?
It's not really
Yeah, that's fine.
It's, basically, I'm working on this thing where I have to send a specific voltage through, and depending on whether it's it's high voltage or it's low voltage, I have to set up a modem and make it go. And that's one side of it. And then the other side is I have to take in a signal in the IR range. And then if it's in that particular signal, I have to either send it to an Arduino or do it like this. And I would prefer doing stuff like this because I want to stay away from coding.
Okay, that's fair. Yeah.
So if you have any recommendations on like books or places to go, I can just.
In terms of resources for this, I mean, if you really want to go in depth with this comparator stuff, you could probably honestly just look at the 2133 textbook. I forget the name. It's book by Cedra Smith. Cedra, S-E-D-R-A, Smith. That's one resource, though it might be a little bit overkill. But yeah. Any other questions? Yes.
Signal just being supplied by those.
Yeah, that's just
And BCC is just used to supply the power to the host.
Pretty much. Yes. All right. Any other questions? All right. Sounds all good. I don't think it'll be a good idea to go through digital to analog, but yeah, pretty much. I guess for those of you that do want to continue on with the notes, so the next part is a digital to analog converter. Right, so what we've looked at is analog to digital. Digital to analog is just the other way around. So for example, that's how we can take the zeros and ones from a computer and output it as, say, maybe sound that you hear in your microphones, well, not microphones, headphones. So that's an example of digital to analog converters. Once again, there are many different ways of creating digital to analog converters, and if you really do want to look at it in more depth, you can check out the 2133 textbook by Cedra Smith, but you can do that in your own time. But yeah, that's otherwise pretty much all of the activities here. So I reckon before we finish up, do we have any last questions about anything we want answered? Yes.
So when we run like programs like measure the voltage of like different nodes, is it like a way to kind of save like the measurements that were placed?
To save the measurements. I'm not aware of any way to save them here. There might be. But yeah.
I think it does work. I'm not sure.
What settings? No. Just a quick look. I can't find anything, but I don't know. Maybe check online. But yeah, when it comes to doing the labs, usually screenshots are the way to go. And also, just to make it easier, oftentimes you can put your screenshots into a Word document as well. So you can type in any annotations there. It just makes it easier for your tutors. But yeah, definitely, like when it comes to your labs, don't open up LTSpice, open up the file, rerun the simulation, pick the points again. Don't do that. Just take screenshots. Yeah. Any other questions? Yes, Joe. Your hairline. I don't have any advice for that, unfortunately. Yep, no worries.
Like if I was taking a particular frequency from a sensor and I wanted to get it into some sort of bit representation to say it's within this band, well, it's within this area, well, band, I guess, sort of, or if that's not a bit. How would I approach something like that where some sort of sensor taking that in?
Okay, so essentially you mean sort of like a comparator except for frequencies, is it?
Yeah.
Ooh, is that not loose? Frequency comparator. I mean, there might be better ways, but the only thing I can think of right now is just essentially maybe using one of the filters that we looked at before, maybe even like a low or high or band pass filter, and then configuring that to with a comparator. So that's just one idea, though it might not take into account the amplitude of it.
Because like, it's sort of the amplitude to be a bit specific, so it'll probably just be like that.
Okay. But yeah, that might be one way. Yeah.
It's just research.
Yeah, no worries. I guess.
I realize that sometimes when you measure like currents, like the arrow sometimes doesn't point towards like the direction I want to, so there's like
Right. Yes. That reminds me, I might just quickly demonstrate something. So, resistor, capacitor, wires. Yeah, so sometimes, like in that case, if the current is in the opposite direction that you want, then pretty much you just on the graph you take the inverse of that, right? So if it's like negative 1 amp in one direction, then it's 1 amp in the other direction, right? Another tip that's just a bit on the not completely related, but let's see. Okay. So, right, so we can look at currents through components just by clicking on the component itself. And you see it gives me this sort of magnifying glass symbol with an arrow through it. In this case, you see on my graph, it's looking at the our current through resistor 1. Something you can also do, on my computer, if you press Alt, you get this kind of thermometer button. What that actually is, if you notice, it's the voltage times current. Pressing Alt is actually a shortcut to finding the power dissipated by a component as well. That's just another trick you can do. Yes. All good. Any other questions? All right. We'll finish off at that for today. So we're running a bit early, but that's okay. But yeah, thanks for coming to this workshop. I hope you guys found it useful. All of the resources are available on Joe Lee's website. You can just search up Joe Lee LT Spice and it'll be like the first results. But yeah, thanks for coming. And